Hello, my name is Christophe de Bruyne, and in this lecture we'll be covering querying RDF datasets with SPARQL. Now, what is an RDF dataset? Well, an RDF dataset is a set of triples organized in different named or the one unnamed default graph. SPARQL is a recursive acronym, and it stands for the SPARQL Protocol and RDF Query Language. It has been a W3C recommendation for a while, but the latest version, SPARQL 1.1, was published in March 2013. And in this lecture, we will focus on the retrieval aspects of the SPARQL query language. So when we use SPARQL to retrieve information, it allows us to, for instance, pull values from structured and semi-structured data, explore data by querying unknown relationships. We can even perform complex query joins over different graphs in a single simple query, and even across different endpoints in a single simple query. Furthermore, it allows us to transform RDF data from one vocabulary to another. In other words, we can create RDF based on the query in terms of RDF. This lecture, a lot of the examples were adopted from either the SPARQL by example tutorial by Feigenbaum and Prud'homme, and also chapter 7 of the Foundation of Semantic Web Technologies book. So let's start by examining the structure of a SPARQL select query, and I will put that down here. There are other types of queries, but we'll start with the select query. So a SPARQL select query follows a particular skeleton, which you can see on the right, and it starts with the prefix declarations. The prefix declarations allows us to abbreviate URIs used in the query, much like the way we use namespace prefixes in RDF serialization. So in this particular example, we bind this particular namespace to the namespace prefix FOV. Then you have the result class, identifying what variables we want the query to return for subsequent processing. Then we have the dataset definition, informing the SPARQL endpoint and what graphs we are looking for information. Then we have our where clause, the actual query pattern, specifying what to query for in the underlying datasets defined in the dataset definition. And finally, we have our query modifiers, allowing us to slice, order, and otherwise rearrange the results in our result set. As I mentioned before, SPARQL queries are executed against RDF datasets, and RDF datasets are sets of triples organized in one or more RDF graphs. Now, a SPARQL endpoint accepts queries and will return results via HTTP. The type of result depends on the type of query. Now, the results are rendered in a variety of formats. For instance, SPARQL specifies an XML vocabulary for the result sets. And then for each result in the result set, values will be bound to the variable names. There is also a JSON port of that vocabulary, which is useful for rich internet applications. Important to note is that certain SPARQL results, or certain SPARQL queries rather, results in responses that contain RDF rather than results. So depending on the query, you might get RDF as a result rather than a result set. Sometimes SPARQL endpoints provide an HTML representation of the results, which is often an XSLT transformation of the XML, and some others support CSV as a result set format. So let's start with a simple example. Here I have a RDF turtle file that uses the FOV ontology, which you can find here. It also avails of RDF and RDFS, and its base has been declared as being http://foo.bar/. Now, what's inside that RDF file? Well, I declare cat being an instance of RDFS class with a particular label cat. I also declare a property owns with a label owns, and the domain is a person, FOV person, and the range is a cat. Then I declare 3 cats, Victor, Gaston, and Bettina. They're all instances of the class cat, and they have their names. And to relate their names, I use the predicate fov.name. And then finally, I declare something Geur de Breu, which is an instance of fov person with a particular name, my name, Christophe de Bruyne, and I own those 3 cats, which you can see here. I will be using that example for a couple of the queries in the next slides. So let's start with a very simple SPARQL query. In this example, we will find all cats and their names. The query looks as follows. So we start off by declaring the namespace prefixes, allowing us to use shorthands, and I have bound the namespace of my example to the namespace prefix x, and then I've also bound the namespace of fov to the namespace prefix fov. In this particular query, I'm looking for values for the following variables, cat and name, but though the values must come from somewhere, so that I declare in the where clause. So I am looking for things that are of the type cat. You can see xcat as the URI of the class cat in my example. And then of these things, I'm also looking for their name via the predicate fov name, and then the names will be bound to the variable name, and the resources representing those cats will be bound to the variable cat. And if you look at these two, I'm looking for things that are a cat, and those things must have a name. So as we will see later on, I will actually exclude instances of cats that do not have a fov name. And if you look at that, the results of this particular thing, which we call a query triple pattern, will be joined with the results of that triple pattern. And what is used to join them? Well, the common variable names. Now, to summarize, you might have already noticed variables start with a question mark, and they can match any term, a resource or a literal, and they can be placed everywhere in a triple pattern. Now, what's a triple pattern? Triple patterns are just like triples, except that any of their constituents, being the subject, predicate, or object, can be replaced with a variable. And you can have 3 variables in a triple pattern. Now, the select result clause will return a table of variables and values that satisfy the query. And finally, A, as you can see here, is syntactic sugar for RDF type, much like in Turtle, RDF Turtle deserialization format. This allows us to avoid the declaration of the prefix RDF in all of the queries, because this is a common one to use in queries. If we were to slightly reformulate this query, we can actually make the query a little bit terse. And again, the notation is quite similar to Turtle, with which you are hopefully already somewhat familiar with. So this is equivalent. We are looking for cats. So we are looking for things that are of the instance cat. And then with the semicolon, we basically say, and we're saying something about that subject. And that subject must also have a name, and that name will be bound to the variable name. So if we were to fire that query, and in this particular instance, I'm availing of Apache Jenna, and Apache Jenna provides us a result set formatter that displays the results in a pretty neat way. You can see that in the example, I have 3 cats. These are their URIs, and these are their corresponding names. To summarize, this query is looking for all the subsets in the RDF dataset that matches these query pattern. Such a subset is called a solution, and then that solution is used to bind values to the variables. You can then choose either to return all the variables or a subset of those. In other words, you do not have to use all the variables or return all the variables in your query pattern. For instance, we could have also looked for all the cats that have a name and that are owned by Christoph. So you might add an additional triple pattern, or owned by a person rather. So we have a person, and that person owns that cat. This will return us the same result because none of the cats in our data set is not owned by anyone. But this demonstrates that you can actually look for patterns with a variable that you're not using here. Now, I did almost make a mistake and I said, well, I'm looking for the cats owned by Christoph. You can also specify that. You can state that you are looking for a specific resource in that pattern, and in this example, that would have been example Jeu de Breu. And if you want to provide a absolute URI, that's also possible with the following notation: HTTP, much like in turtle bar / Jeu de Breu. Now for a different example. We will use a query that is somewhat similar, but we will fire that query to DBpedia. DBpedia is an effort to, let's say, triplify Wikipedia, and they provide us a SPARQL endpoint. And in this example, we will be looking for 50 things with names in DBpedia. So how do we go about doing this? Well, I will now, from now on, I will most of the time omit the namespace prefixes, even though I have provided the full URI of FOVName here, but that's fine. So we're selecting agents. We're looking for things that have a name, and we're selecting things bound to the variable agent, and they must have a name. And notice that I'm not even using that name in the result set. So I'm looking for agents that have a name, and I limit the result set to 50. So we hope that we would obtain 50 resources that would be bound to that variable. And in the case of a resource with a URI, we will get the URI. In the case of a blank node, we will get an internal identifier. But something is wrong. You might think that it will return 50 distinct things. However, if an agent has more than one name, it may happen that that agent will appear multiple times in the result set. And this is what you can notice here. We will be firing the query in DBpedia, and we notice that we have the same resource appearing multiple times. We have duplicates in the result set. And why is that? Well, it's because those resources have more than one FOF name. So how do we get 50 distinct agents that have names? Well, we need to include a new construct in the query. And it's quite straightforward. We will be selecting distinct values of all the variables appearing in our select class and then limit it to 50. And that's how we solve this problem. So now it will look for all agents that have names until 50 are found, or until it has looked at the whole data set and was unable to find 50 in the whole set. Now, limit 50 is what we call a solution modifier. Limit allows us to limit the number of rows returned in the result set. Then we can also avail of order by, which allows us to sort according to the variables in ascending and descending order, according to the variables appearing in the select class. And then we also have offset. And offset can be used together with limit and order by for slicing. Slicing is paging. So you can say the first 100 and then the second 100 and so forth and so forth. Here's another query. In this particular query, we will introduce a new concept called filtering. Filtering allows us to formulate conditions to filter out unwanted results. So we will formulate the conditions that all the patterns have to, or all the possible solutions have to meet in order to be retained in the results set. So in this particular example, I'm availing of the RDFS namespace, the DBpedia ontology, and the Yago ontology, and I'm looking for country names and their populations. And those variables are going to be pulled from this particular var class. I'm looking for countries, things that are of the instance WikiCat landlocked country. And I know that those things have a country name attached to them with RDFS label. And I'm also looking for their population total if it exists. Well, not if it exists, it has to exist, otherwise it will not be included in the result set. However, I am looking for those countries where their population is bigger than 15 million. So if we were to have a country that is a WikiCat landlocked country, and it has a name and it has a population, but that population is smaller than or equal to 15 million, it will not appear in the result set. And again, I demonstrated here the semicolon because this is a shorthand. I'm asking for triple patterns about the same subject. If we were to fire that query, however, again, we have a problem. Why? Well, Afghanistan has multiple names, and that is an issue. So for every match that you have in one of the triple patterns, you will have an inclusion in the result set. So in this particular example, if a country has 20 names and it has a population and it is of the type WikiCat landlocked country, it will be included 20 times in that result set. Now, we cannot do a distinct here. Why? Well, we are selecting the country name. So the distinct will not work because Afghanistan in English and that value is different from Afghanistan in German and that same value. So the result sets are distinct. how do we go about and solving this? Well, let's say that we are only interested in English labels. So we need functions. SPARQL provides us with a couple of functions that we can use in those filter clauses. And they can be logical. So you have your not, and or logical operators. You have your arithmetic operators. Then you have a couple of comparison operators. You have equals, different from, lower than, and so forth. In a set, not in a set, and so forth. Then you have some SPARQL tests. You have a test to check whether it's a URI, whether a thing is a blank node, whether a thing is a literal, is numeric, whether a variable is even bound, which we will see later on. And then you have a couple of accessors. Given a variable with a value, what's the string? What's the language of that string if it has a language? What's the data type? And then there are a couple of other functions that you can avail of. Same term to check whether two variables refer to the same RDF term. You have lang matches to check whether the language matches a particular value, such as English. You have regular expressions, you have replace and whatnot. And ever since SPARQL 1.1, even more functions have been included. You can now include conditionals, if statements, or exists and not exist to filter out things that meet a particular criteria. You also have constructors. You can create URIs, blank nodes, and so forth on the fly. You have string functions, you have additional math functions and whatnot. You get the gist. So let's now use this to only include those countries for which we have an English label. How do we go about doing this? Well, we add an additional filter clause. We want to filter those countries who have a label, country name, of which the language, and we use this accessor, lang matches English. And this is according to a particular standard, and you can check whether it's English or Dutch or French, and you can even go as far as saying Irish, English, and whatnot. Now, you can see that the result now contains for each English label a population. The downside, however, is this assumes that the countries that you retrieve have an English label. If you were to have a country, for instance Belgium, and in that data set Belgium doesn't have a label tagged with as being of the English language, then it will be not withheld for the result set. And I will reiterate that. Given this query makes a couple of important assumptions. It assumes that all landlocked countries are typed with Yago Wikicat landlocked country. It also assumes that all countries have an RDFS label, and that RDFS label is of the English language. And finally, it also assumes that all landlocked countries have a population that is numerical via the property DBO population total. Otherwise, if it's not numerical, you cannot do the numerical comparison. Now, finally, what this slide demonstrates is that you can combine the two conditions with a logical operator. In the previous slide, we had two filter statements. Here we combine them into one using ampersand, ampersand. Now, let's say, for example, we have an RDF dataset with 20 cats. And of these 20 cats, 15 have exactly one name, which is of a type fov name. Sorry, not of the type fov name, but related by the predicate fov name. Okay, assume that I want to retrieve all instances of cat. Well, how do I go about doing this? Well, I will select a variable name and I will give it a meaningful variable name, cat, where, and then I have my query pattern. I will now introduce a triple pattern, and the triple pattern is as follows. I want things of the type x cat. Now I do assume that the prefixes have been declared above. With that query, I will obtain the 20 cats. Now, if I were to retrieve all the cats that have a name, then I will just add the following triple pattern to the query. And I do not even include the variable in the select clause. So I'm looking for all things that are a cat, and those things must also have a fov name. The result will be that I have 15 cats, because I know that only 15 cats in my dataset have exactly one name. If cats could have multiple names and I'm only interested in retrieving the cats that have a name, then as we've seen before, we can add distinct here after the select word, but in this particular case, that's not necessary. Now, if I'm interested in only those cats that have a name that is longer than 5 characters, I need a filter statement. So I will filter those that meet a particular condition, and I know that there's a function strlen, which stands for string length, and I will ask the length of that name, and it has to be bigger than 5. Great. So if 10 cats have a name that is longer than 5 characters, those will appear in the result set. Now, I might be interested in sorting those cats by their name, so then we will order by their name, which is by default ascending. So you can make it explicit, but that's not necessary. And if you want to have them descending, you has to be DESC descending, and that's how you have to order them by their name in descending order. So what I wanted to convey with this example is that the addition of additional triple patterns constituting the graph pattern has as an effect that you constrain the conditions a bit more, and you constrain the conditions that these solutions have to meet by placing additional filters inside that graph pattern. Now we will be covering additional constructs that demonstrate how powerful and expressive SPARQL, the SPARQL query language, can be. The first construct that we will cover is the union operator, and the union operator allows us to match alternatives, and you can then combine 2 or more graph patterns into one result set, and it is not restricted to triple patterns. So in this particular example, we are combining the results of this graph pattern, which only contains one triple pattern, with the results obtained with this graph pattern. And you can see that in this example, we use the same variable names, but not the same predicate. What happens if we try to fire this? Let's exemplify the union operator. So in this RDF file, we have a couple of statements about 3 books. The first book has a title and a creator, Alice, and it uses a particular vocabulary, Dublin Core 1.0. The second book has also a title and a creator, Bob, but it uses a different vocabulary, Dublin Core 1.1. And then we have a third book, which doesn't have a creator, but its title is provided by both a Dublin Core 1.0 and a Dublin Core 1.1 title, but and moreover, they have different values. Notice that all these books have no URI, they're blank notes. So what are we trying to do? We want to select the titles of these books, but we know that these titles are captured using different vocabularies. So we are looking for books that have a title using Dublin Core 1.0, and we will combine it with another graph pattern looking for books that have a title with the Dublin Core 1.1 vocabulary. And then we will create the union of these two solution sets. And of the combined solution, we will only retain the title. So if we were to fire that, we would see that the title contains 4 values. There are 4 values, 4 solutions, and 4 values for the variable title. We have SPARQL protocol tutorial, we have SPARQL, we have SPARQL updated, and then we have the SPARQL query language tutorial above. What if we were to change the variable names and we change the title in the first pattern by X and the title, the variable name title, by Y in the second graph pattern, and then we were to select both of them in the select clause? Well, what will happen is, and first, order has no importance here. So this just happens to be in that order. It can be different. However, we will see that for X, there are 2 values. And whenever there's a value for X, with respect to this example, there's no value for Y. And conversely, whenever there's a value for Y, there's no value for X. It's non-existent, or NULL would be the equivalent. So you can use the union operator even when the variable names are different. What will happen is that for every variable appearing in the union, that for every variable that has no value, well, there will be an NULL, no value will be provided. So we've seen that using the union operator and different variable names in the operands of the union operator, we could end up in a situation where variables are not bound. And this provides us a nice introduction to the other operator, optional. And you can, if you're familiar with relational databases, you can consider optional as some sort of outer join. And you will see why. What does optional do? Optional tries to match the graph pattern, but doesn't fail if it cannot find values that match that pattern. And if it doesn't fail, and it cannot find something, well, the variables are just not bound. For example, in this particular example, I'm looking for the names and mailboxes, or the email inboxes. And I'm looking for things that have a name, and those things have optionally a mailbox. And if they have a mailbox, it will be bound to the variable mbox. Now, if a person has a name and a mailbox, both values will be bound with their respective to their respective variables. If, however, there's a thing that has a name but not a mailbox, only the name will be bound to that variable. Let's use the optional operator. In this example, I have two blank nodes. They all describe a person. The first person is named Alice and she has two mailboxes. The second person is named Bob and Bob doesn't have a mailbox. Once we fire that query, we will see that there are three solutions in the result set. Why three? Well, Alice has two mailboxes and therefore she will appear twice, once for each mailbox in the result set. Bob also appears in the result set, but there's no value for his mailbox, so it will be null. Now, some details about the computation of the union and the optional in the SPARQL query language. The union operator is both associative and commutative. Basically, that means that whenever you have a pattern as follows, you have a graph pattern A, you do the union, graph pattern B, you do the union, graph pattern C. Well, it doesn't really matter where you put the bracers. They can be here or they can be there. They're all equivalent. Furthermore, it is commutative. So if you have, for instance, here you see, let's call that A, and let's call this B, let's call this C. Well, we have A and B union, which corresponds with or C, and that's equivalent with A, B union A, C as a pattern. In this example, I exemplify that. Now, if you want, you can add curly braces to improve readability, but that just causes additional overhead because those characters will be sent to the server, and you might win some bytes by avoiding that. So in this particular case, you could add curly braces here, but this is equivalent, but it doesn't change anything. But it might be improve readability if you want to. Now, for the optional is left associative, so that's a bit trickier. So here we have an example. Provided that you have a pattern followed by two optional patterns, well, that is equivalent with from left to right, combining those with graph with curly braces. So you are allowed to do this, but you're not allowed to start combining from right to left. And you can find details on of that in papers and documentation, but it all has to do with the binding of values to variables and how you can have slightly different results if that would be the case. Now, because of that, here's an example. Here on the left, we have an example of a graph pattern where we have one triple pattern and two optional triple patterns. And what I want you to notice is that the first optional is looking for a author, and that value will be bound to A. And then the other optional is also looking for something, a writer, and it will also be bound to A. Now, what will happen here? Suppose that for a particular book X, there is an author A, Christophe de Bruyne, and that is found. Fantastic. But then that value will already be bound, and any other value for writer that is different from A will not be found. So whenever this value, because it's left associative, so this one has precedence, whenever there's a value for this one, it doesn't have, it might miss values that you can find for the second one. Usually, unless you know what you're doing, having multiple optionals with shared variables, so outer joins where you're looking for the same value, that could be questioned. So a pattern that you're more likely to find is the following, where you have two outer joins and you will bind the values to two different variables. Again, similarly, you can avail of additional curly braces to improve readability at the expense of overhead while exchanging the query between the server, between the client and the server. Now, watch out. Apart from bound, all functions and operators that operate on RDF will produce a type error if any arguments are unbound. So a simple test, like you want to test whether a variable is different from a value, they're not sufficient. Why is that? Well, because whenever a value is unbound and you apply an operator or a function to either operand being unbound, you will raise an error. And because of that error, you have a three-valued logic. So here's a truth table. So let's assume that we're looking for a operator. Let's test something, whether it's the OR. Well, you want to retain everything that is true. So whenever one of the operands is true, in the case of OR, you will have that it's true. And here both of them are false, and hence it's false. But the evaluation of a particular condition here can also evaluate to error in case one of the operands is unbound. So you also have to check what in the case if one of the operands is error. Now for the OR, it's pretty straightforward. From the moment you have one true, it's true, but in the other cases it defaults to error because there's an error that is raised, and hence if you compare an error and a false, you will raise an error. In practice, that means you have to watch out when using variables declared in an optional pattern outside said optional pattern. For example, assume that we have an RDF dataset containing cats and that some cats have no name. So we want to retrieve all the cats that have no name, or when they have a name, then that name is longer than 5 characters. A common mistake would be to do it as follows. You see that we're looking for instances of cats. Then in an optional pattern, we declare looking for their names, so an outer join. And then outside the optional pattern, we check whether their name is longer than 5. Now, when a cat doesn't have a name, that value will not be bound. And when that cat's unbound name is applied to this function, you will get, I will use green, error, because the length, applying the length function to an unbound variable results in error. And then the whole comparison also evaluates to error. And because the filter only retains all the solutions that satisfy the criteria, and this particular condition evaluates to error for cats without a name. Cats without a name are not withheld in the result set, so not our desired result. So even cats without a name are not included as functions evaluate to error. To solve this, you just have to move this pattern inside the optional clause as done here. And now in this particular case, we retain all the cats. And if those cats have a name, well, then that name must satisfy that particular criteria. Now, of course, if a cat has more than one name, only the names that are longer than 5 are retained. And in this particular case, if a cat has more than 2 long names or more than 1 long name, well, obviously you should put a distinct here. But this example just demonstrates the issue when of using unbound variables outside the optional pattern. We already discussed that SPARQL is a query language to query RDF datasets. That means that triples are organized into graphs. And there's the so-called unnamed or default graph, and the other graphs are so-called named graphs. They have a URI. They are identified by a URI. In this particular example, we are querying from a particular data set all the people that have occurred in at least 3 different conferences. So in this particular example, I'm looking for names, names of people that have been declared in the default graph, because you don't see a graph pattern there. And that person, for each event, there's a separate graph, and that person must have appeared in 3 different graphs. So we're looking for graphs with a URI, and you can see we can even replace the URI of a graph with a variable. And we're looking for the same person in 3 different graphs. Now, if we are not careful and that person only appears in 1 event, well, then that 1 event will be bound, the URI of that graph will be bound to G1, G2, and G3. So we filter out all the solutions that share the same URI or the same value for these 3 variables. So we filter those that have a different value for G1 and G2, a different value for G1 and G3, and a different value for G2 and G3. And that's how we obtain people who appear in at least 3 different conferences. And if they appear in 4 or 5, well, that doesn't really matter. Now, that means instead of triples, we have quads. And typically those graphs serve as a context. You can, for instance, have graphs for different events, different dates, different documents, and so forth and so forth. And you can do all sorts of neat and clever things with those. Now, knowing that we have these quads, you can inform the endpoint on how you want to use these quads to look for information. And in the query, we have 2 types of clauses. Now, if we don't provide any from or from named clause, it's going to look in the default graph for regular triples, or you have to explicitly look for the graph patterns by providing the graph URI. Now, the from clause refers to the default graphs that you will create, and the from named clauses to the clauses refer to the named graphs that you're explicitly listing. Now, if you provide from named clauses without a from clause, the default graph is empty and assumed to be empty when you use it. We will exemplify that with an image. This particular image, you can clearly see what we're doing. We are querying something, and we are creating the default graph from G1 and G4, sorry. And then we are using 3 named graphs, G1, G2, and G3. And there might be others inside the triple store, but we discard them. We don't care about them. And whenever in our query we are looking for triple patterns without the graph declared, well, we are looking for those triple patterns in the default graph, being the union of G1 and G4. But whenever we're looking inside a graph, and either by explicitly, oops, that's too dark, either by explicitly referring to a resource or with a variable, well, then we are looking into the named graphs. So in this particular case, we are looking explicitly in this graph. And because for this graph pattern, we added a variable name where the graph URI could have been, we are looking for these patterns inside the 3 named graphs declared here. And it's easy as that. Now, if no from clause would have been declared, well, then the default graph is considered to be empty and nothing would have been bound here. We have now seen a couple of examples of SPARQL select queries. SPARQL also provides a construct query. And a construct query is used to create RDF graphs based on a query. And typically they're useful to generate one-step transformations between vocabulary. So you query, you look for solutions based on patterns, and then you use these solutions to create a new RDF graph and maybe using a different vocabulary. So let's go back to the example of my cats. So I had 3 cats and declared me as a person owning these 3 cats. Now, I know that in the FOV ontology, FOV person is a subclass of FOV agent. I have not declared my cats to be an instance of FOV agent, but I know that they are because they have a FOV name and only FOV agents can have a name. I'm not availing of reasoning, but I want to construct a list of agents based on a query. So what I do here is I'm looking for all the cats and I'm looking for all the people, and I share the variable agent for this union. And then all solutions, all values bound to that variable agent will be used to construct the following triple: value of variable a FOV agent. When I apply this query to my data, this is the result. I have 4 triples stating that Bettina, Victor, and Gaston are FOV agents, as well as me, Gudebru, being an instance of FOV agent. Another type of query is the SPARQL ask query, and that just returns true or false. A SPARQL ask query can be used to assess the existence of a solution. You're not retrieving the whole solution, you're not retrieving all the solutions, you just ask, is there a solution? For instance, here we ask, do we have cat owners? So I ask where is there a person that owns something, a cat? If such a triple were to exist, at least one, the value will be true. And finally, an interesting query is the SPARQL describe query. Whenever you use a describe query, the server will return all the triples that describe that resource. The only caveat in this setting is that the server decides what RDF to return describing a resource. And one needs to be careful because the description, as explained in the SPARQL W3C recommendation, the description is determined by the query service. So if we were to formulate a describe query and we ask the SPARQL endpoint to describe cat where all the cats have the name Victor, so we're looking for all the cats who have the name Victor, and for all these solutions we ask the SPARQL endpoints to describe that one, well, then we get the triples describing Victor. And in this particular example, we have all the triples where Victor is the subject. We know that Victor is a cat and Victor has the name Victor. The recommendation states that you should at least return the triples of which the resource is the subject. That's something you can rely on. But some implementations do provide you the so-called backlinks, all the triples that also feature the resource as being the object or even the predicate. Finally, a couple of nifty features of SPARQL. Projected expressions. Sometimes we need to compute new values based on our solution and bind them to a variable. And there are two ways of going about it. One is by doing so in the select clause. So I'm not a chemist, but what we're trying to compute is the neutrons of elements by deducting the protons from the weight. And how do you go about doing this in the select clause? You just you put the computation inside parentheses, and then you have your computation here. You can even use functions and whatnot. And then you bind them to a variable using the as construct. Another feature we want to that I wanted to show here is the use of unnamed variables. The syntax is similar to the blank note syntax of Turtle, but this basically means we're looking for something, but we don't want to assign it to a variable name. So we're looking for something that is an element that has an atomic number, that has a weight, and that has a name, but we don't want to assign that resource to a variable. So, as I stated, the square brackets are used as unnamed variables, much like the underscore in Prolog. Another way to assign computed values to variables is with an assignment using the bind directive. And these do not appear in the select clause, but they appear in the body of the query by merely using the bind directive and then putting the computation inside the bind directive and again using as to assign the value to the variable name. Projections are often used together with aggregates. Much like SQL or SQL, you can group solutions by certain variables so that you can compute averages, minimum sums, and whatnot, even sample. And in this particular case, we're looking for things that are of the type road, and we also know that roads have a particular category, count point road category. And then we will select the category and count the distinct things as the number of rows. So we will count the number of rows for each category. We will soon cover a couple of the aggregate functions that are typically used in SPARQL. So these aggregate functions are similar to SQL, and you have your run-of-the-mill functions, count, min, max, sum, average. Two of my favorite ones are group concat and sample. Group concat is used to concatenate all the values that you have aggregated in a particular way. So you could create a list of names, for example. And sample is an often overlooked one. Assume that you have cats, and cats can have multiple names, but you want to group by cat, and you only want to use one name, but you're not really interested in which one. Well, the sample function will return for an aggregate a random one, just one. So if your cat has 3 names and you group by cat and you only want one name, you sample, it will return one of the 3 names. I find this one particularly useful when generating values for an interface, and I just have many names, but I'm only interested in just one of them. Also, the introduction of the having clause to filter the results is made available. You have that, so you can test having max, for instance, price bigger than 5,000. That's available as well. And then another interesting feature is subqueries. Subqueries allow you to embed other queries and use these to compute a much more complex query. So you basically formulate a query in terms of smaller queries. Let's discuss this with an example. So the goal is to retrieve the second page of names and emails of people in Tim Berners-Lee's profile, given that each page has 10 people. Okay, so once we try that, we might assume that the query might look as follows. We're looking for people that have a name, and we know that not all people have an email address, or you do not have the email address of everybody, so it's optional. And then we will order the people by their name, but we want only 10 people, and we offset it by 10 because we are interested in the second page. However, so this process is called slicing. However, this query is not entirely correct. Why not? Well, we're going to show the second 10 solutions in the result set. But what if you have people with more than one email address? They will appear that number of times in the result set. So how do we show 10 people and their n more than one email addresses, if they have more than one, or 0, on the second page? Well, we need a subquery. So here you can see that this particular person has 3 email addresses, and then you have a couple who have none, and here they only have 1. So this is not what we desire. Well, we will be using subqueries. Inside our where clause, we will create a subquery which has to start with an open curly brace and a closed curly brace. And inside those curly braces, we create a new select clause, a new where body, and all the query modifiers and whatnot. Here we look for distinct people and their names where they have a fauve name. So we look for people and their names, and they have to be distinct. and we order by their name, we limit to 10 results, and we have an offset of 10. So in other words, here we are looking for the second page of 10 people and their names. But now we also want their email addresses. We fetch their email addresses with this optional pattern. Remember, not all people have an email address. But now, since some people have more than one email address, we will be able to obtain those. So this is the outer join. We will outer join the results of this subquery with this optional pattern, and we will be able to obtain the second page of people. We currently looked at query patterns where we added constraints. With each triple pattern that we add and each filter that we add, we constrain the number of possible solutions, unless we avail of constructs such as union, which provides us alternative paths. But actually, whenever you add something, you look for things that exist. Now, we will be covering negation. How do we obtain things for which something does not exist? In SPARQL 1.0, there was the filter not bound pattern, which roughly corresponds with negation as failure. Now, the goal here is to use the optional pattern to do some sort of outer join, and whenever a variable is not bound or not bound to a value, well, then you will check whether that value is unbound. And if that's the case, then you filter it. So in this example, we want to find the people that do not have a URL associated with the RDFS see also predicate. We are looking to select their names, and we're looking for people and their names. And again, you might see that we're availing of a variable that we do not use here in the select construct. Then with the optional pattern, we are looking for the RDFS see also statements of that person. And whenever that value or such a value wouldn't exist, well, then that variable would be not bound. And we have a function that checks whether a variable is bound or not, and that is the bound function. And we will negate that. In other words, whenever there's no value assigned to URL, the function bound will return false, but the negation of false is true. And because the filter statement will only withhold all the solutions that satisfy that condition, well, then all the people without an RDF see also statement will be kept. And that's one way of going about this. Now notice that I only use name here. If I had provided the URL variable there, well, none of the solutions would have contained a value for URL. So it doesn't really matter to include that in the select clause. Now, SPARQL 1.1 introduced two new ways of dealing with negation, and that is the minus operator and the filter not exists condition. In the first, we will cover the minus operator. So the minus graph pattern is a binary operator where you remove bindings from solutions in the pattern on the left hand side, this one, with bindings that match on the right hand side and for which there are shared variables. And this is quite key and this is important to note, shared variables. So in this example, these two triple patterns will provide us all the solutions of people and their names, but then it will look for people and their see also URIs, and then remove all these people based on shared variables between or shared bindings between these two variables. With filter not exists, on the other hand, you're looking to remove bindings from the solutions by testing for the non-existence of a pattern. And in this particular example, it looks as follows. Again, we are looking for all the people and their names, and then we test. Does the following pattern, that person has a see also statement with a URI, does that pattern not exist? And when that is true, we withhold that particular solution. Now, both of them are in the most cases similar, but there's an important nuance. The not exists and minus represent two different ways of thinking about negation, and in most of the cases you get the same results. The not exists is based on testing whether a pattern exists, and when it exists, you don't include it in the final result set. Now the minus represents a negation where you remove solutions based on the evaluation of two patterns, and you remove the solutions from the left-hand side by looking for same values in shared variables. And again, I will put this here between parentheses, shared variables. And as I said, in most of the cases, they produce the same results. However, there are some corner cases that can produce different answers, and I will exemplify that on the following slide. Let's take this very simple RDF dataset. We have no named graph, and we just have one triple, ABC. In the first one, we use filter not exists, and notice that we have, for the first triple pattern, three variables, SPO, and in the not exists pattern, we have different variable names, XYZ. If we were to execute that query, we would have no solution. Why is that? Well, the XYZ matches any pattern. So while this one corresponds with ABC, this one also corresponds with ABC, and therefore this solution, ABC, for this query pattern has been removed. So it eliminates any solution. In the second case, we would have a result. Why is that? Well, there are no shared variables. So this one matches a pattern, solution, ABC. This one also matches with ABC, but since there are no shared variables, nothing has been eliminated. Now that we have covered negation, I want to talk about property paths. Property paths allow you to query arbitrary length paths throughout the data set. And why I find that interesting is it provides you a way to do some what I would like to call syntactic reasoning. If you are aware of how your data is structured, you can avail of that knowledge to create very expressive queries. Let's look at a particular example. We know that we have an ontology and we have a class. We have beer as a class, and we might have several subclasses. And we don't know how deep that taxonomic tree is. And the class hierarchy is captured with RDFS subclass of. Now, if we want to find instances of beer, we can use the following triple pattern. Give me everything that is of the type beer. And everything that is explicitly stated as being of the type beer, so we have an example 1, a beer, will be captured by that triple pattern. However, we might have another beer, x2, which is being declared as being an instance of that type of beer, this one. Now, that particular triple will not match with this triple pattern. However, we know that there are subclasses of beer. Property paths allow us to declare the path of properties between the subject and the object. So if we want to find all instances of beer or instances of subclasses of beer, we can avail of the following property path. It is an RDF type statement followed by 0 or more RDFS subclass of statements. And with this particular pattern, we will match both we will get both example 1 and example 2. Why? Well, here we have an immediate RDF type relationship and 0 subclass statements, so that is covered. And in this particular one, we have 1 RDF type statement followed by 2 RDFS subclass of statements. Now, in this particular example, we assume that the ontology itself is also available in the RDF dataset. But as I said, it allows us to do some syntactic reasoning over the graph. This is not real reasoning using an RDFS reasoner, but as you can see, we can use the knowledge of the ontology to obtain a wider range of beers by exploiting, as it were, the taxonomy in this particular graph. In the next few slides, I will provide you different examples of property paths. So property paths allow you, we've seen that we can get 0 or more of a particular predicate in between two resources, but property paths allows us also to formulate alternatives. So in this particular example, we are looking for titles or labels, and we will be calling those display strings. And they are either obtained by looking at the DC title predicate or RDFS label. So as you can see, this is a OR. So we can get alternatives. And if a particular book were to have both of them, well, we would get the two results. Now, in the other example, we want to find the name of any people that Alice knows. So that's a sequence. So we are looking for all the names that Alice knows. So we will assign the resource identifier or blank node identifier of Alice, but because she's identified with this email address. And we are going to look for the names of the people she knows. So basically we are looking for people, and remember the range of the both nodes relationship is a person, and we are going to look for the names of that person. And we effectively we got rid of the intermediate variable if we were to put that in. Now we can extend that. They can be of arbitrary length. Find the name of any people known by someone that Alice knows. So the names of people known by people that Alice knows. This looks as follows. You know, similarly, we select Alice as such, and then we know that Alice needs to know people, and those people need to know people, and they have a name. And we can rewrite that query so that you can see with what that corresponds with. This is the same as stating we're looking for Alice, and Alice knows a particular person, and that particular person knows another person, and that other person must have a name. And here you can clearly see that in this particular case, we got rid of the intermediate variable names. It's not necessary anymore. Now, we can also rewrite this without explicit variables, but without using a property path. I just want to demonstrate this just to illustrate the capabilities and the expressive capabilities of SPARQL. In this particular case, I'm availing of the square brackets that denote a variable that has no name. And what I do here is I'm looking for people that Alice knows, but I don't want to assign these values to a variable, so I avail of these square brackets. And in this particular case, I constrain the pattern by declaring patterns inside the square brackets. And the patterns inside the square brackets do not have a subject. In this particular case, you can see that this person is the subject, and I'm looking for a triple pattern that matches both knows and another person. And similarly, this other person is the subject, will be assigned to an unnamed variable, if we can call it that, but we further constrain it by looking for a triple pattern, both name with a name. Again, this is a different way of writing it. They are equivalent, but property paths might be a nice, elegant way to make your query a little bit more terse. Now, I haven't covered all of the capabilities. You can find those in the W3C recommendation. Capabilities include a shorthand notation for inverse. So if you're interested in people that know Alice, but not necessarily know, and that Alice not necessarily has made explicit that she knows, well, you can do the following. X, and then you would have both knows somebody else, right? This is the inverse of both knows. So you're actually looking for Y both knows X. Finally, something that I want to cover are federated queries. What are federated queries? Federated queries are queries that avail of external services, often a SPARQL endpoint as well, to fetch solutions. In this particular example, we are looking for books and their title, and we want to know their creators. So maybe in our data set, we only have titles, but we don't have the authors. And in order to fetch the authors, we have to avail of an external service. And then with the service keyword and providing the URI of that service, which is often a SPARQL endpoint, Then we will consult this endpoint or service to look for the creators. So we're looking for a different resource and we have to use a different variable name because the URIs might differ, but we know that it has the same title. And once we find a book with the same title, we look for their creators and then we return the creators of those books. So in this particular query, we get a list of all the creators of all the books we have in our data set. If we want to have the list of creators and their books, we just have to add the variable b in our select clause. Now, because we provide patterns here, most naturally, those services are SPARQL endpoints. But our engine that processes this query will not make any such assumptions. It only assumes that it will do a SPARQL call. It will fire off this SPARQL query to the SPARQL endpoint, and it expects a result in, for instance, the XML representation of the solutions and their bindings. So you can see or create a scenario where this is an interface that is capable of understanding this request, but is not necessarily a SPARQL endpoint, but does return valid results that correspond with the behavior of a SPARQL endpoint. Here's another example of a SPARQL federated query. At the time I created that query, it was possible to run this query on the Ordnance Survey UK SPARQL endpoint. And in this particular example, I'm looking for things and their label, but I'm consulting the DBpedia SPARQL endpoint inside that service. And I'm looking for things that match their label. So I'm looking for matching labels, and whenever I find a match, I will return everything. So if I find things that have the same label in my dataset or in the Ordnance Survey UK's dataset and DBpedia, I will just return those matches. Now I did limit it to 2. Why? Because DBpedia is quite a massive dataset, and so is Ordnance Survey UK, and it took a while to load. Now, this is one of the problems that can occur, the massive amount of overhead, not only in terms of query evaluation, but also when you are dealing with enormous data set. But you also have to remember if you make calls to data sets that are hosted elsewhere, there is additional network overhead as well. Now, to summarize, in this particular lecture, we focused on 4 types of information retrieval queries, being the select clause, where we choose either all variables or a subset of the variables used in a query pattern to find things, or well, to find things in our RDF dataset. We also have covered the construct query pattern, where we will create RDF graphs based on solutions found using a query pattern. We've also covered the describe query pattern, where we will return descriptions of resources of the variables that we select in our query pattern. And then we also have seen the ask query that basically returns true or false when there is at least one solution for a query pattern. I did focus on the use of named graphs because I find that important, and we also covered aspects such as property paths, negation, the use of union, and the optional in SPARQL queries. What we have not covered in this lecture are SPARQL update, the graph store protocol, service descriptions, entailment regimes, and so forth and so forth. These will be part of another video.